We are the Cyberglove team, and this is our final demonstration. I'm Wyatt Smith.
I'm Reagan Deal.
I'm Hunter Atchison.
I'm Dakota Price.
Start with a brief summary of the project description.
So for our customer needs, what we needed to provide was a sensor apparatus of some kind that receives data on the motion of a human hand and fingers and relays that motion to a virtual or mechanical hand. Because of the COVID-19 environment, we decided to do a virtual hand, and that virtual or mechanical hand had to mimic the human hand and fingers.
So our project goal was to capture the hand motions with the sensor apparatus and then mimic those movements with a virtual hand. There are plenty of applications out there for something like this, anything from a gaming system to virtual reality or training environments. And then also there are lots of solutions out there that do this in some form, but we were focusing on getting the general capabilities at a low development budget.
The objectives of our Cyberglove is to create a system of sensors to capture the motion of a human hand and fingers, to build the system sensors into a wearable apparatus for a human hand, create a virtual output hand that models a human hand, design hardware to collect the sensors information from the input as motion data, to build a communication relay from the motion data to the virtual hand, write code to interpret the motion data as control signals for the virtual hand, and to implement the motion data to mimic the movements of the input hand to the virtual hand.
For functional requirements of the system, the sensor apparatus shall measure and the output hand shall rotate at each joint. As you can see, we have supination and pronation of the wrist. We have the flexation of the wrist up and down with 90-degree angles. You have to have finger extension in order to be able to make a full fist, and the roll and yaw of the hand, as well as the pitch. The output hand has to be able to mimic these movements and produce a replica hand.
Our performance requirements were that the sensor apparatus shall measure a range of angles of the actual hand. You can see those in the table here. Also, we had a requirement that the communication interface between the input and output shall act in real time.
For our operational requirements, the sensor apparatus shall be worn by an average-sized human hand. The sensor apparatus shall not interfere with user hand motion. We really didn't want the glove to be too tight or just really have any restrictions on any hand movement. The power shall be necessary for the system to operate using either a duplex outlet or possibly a rechargeable battery. We decided to use the input from really a PC USB connection. A PC with Unity 2020.3.3F1 shall be necessary to use the virtual hand. We did use this version of Unity, so our hand will not be able to be used in a different version. The system shall be able to operate indefinitely in an indoor laboratory environment, and the sensor apparatus shall not expose the user to voltages of more than 12 volts. And now we're moving on to our summary of our final design.
Our final deliverables for this project is our operational prototype is a wearable sensor apparatus which uses software to register hand movements and a virtual output hand, as demonstrated on the right hand side in this little video here we have. Our final demonstration is a display of our finalized prototype to the capstone class, and our documentation is a technical report and operational guide for the entire system. Here we have just the general hardware map showing our sensor apparatus and how we have our glove that sends our information of the hand movements to the communication interface, which sends the hand movements to the virtual hand, so you're able to move at the same time as the virtual hand is moving.
And this is a software map of each subsystem. So you have the sensor values coming from the sensor apparatus, and then the COM interface performs a few functions on that and sends it over to the virtual hand.
here is a more in-depth look at what our sensor apparatus ended up being like. As you can see, those pictures to the side of the hands represent what the actual sensors look like, but we did use flex sensors for the finger movements, and SparkFun actually had these quick flex glove controllers that allowed us to use I2C bus to connect to daisy chain the two glove controllers together with two IMUs that got the rotational data for the wrists and those movements. And then the flex sensor for the thumb is a analog connection with a resistor circuit on top of this quick shield over here on the right that laid on top of our microcontroller.
For the communication interface, we utilized Arduino resources, including pre-built libraries, to allow access to the IMU and flex sensor data so that we could get the necessary data from the flex sensors along the fingers and the two IMUs on the wrist and the hand. Finger measurements are mapped within Arduino code between 0.0 and 1.0, which are then scaled up by 1,000 to allow it to be easily communicated across from Arduino to Unity. Measurement data is then interpreted by the Arduino code and transmitted to the sister process found in the C# code in Unity. Wired communication transmits data through the USB to micro USB port from the microcontroller to the Arduino program.
The final subsystem is the virtual hand, which is responsible for receiving data from Arduino, converting data to control signals, and controlling the hand model. Like Hunter said, we use Unity for this, which uses C#.
This is our sensor apparatus, like put together. You can see in that picture on the right. And we did use the flex sensors and the IMUs to capture the hand motion data. For implementation, we have the one analog flex sensor on the thumb, the two flex glove controllers to gather the data for all four fingers, and the two IMUs, one right there, like on the wrist, and then one a little bit up on the forearm. And some unforeseen issues that we had, the quick shield that lays on top of the microcontroller didn't work exactly how we were expecting. It was meant for the Arduino Uno specifically, so we had to wire things around a little bit different to get it to work. And then our flex sensors were very noisy. We knew that they would have noise associated with them initially, but they had more noise than we expected them to. And our IMUs had connectivity problems. They weren't starting up every single time that we ran our program, and we just didn't have enough time to really figure out the issue for that.
For the design of the communication interface, the implementation included the microcontroller that reads the analog flex sensors through the voltage pins. The microcontroller also reads the two flex controllers and the two IMUs with a shared I2C bus. To smooth the noisy data that we mentioned in the previous slides, we used a moving average in the Arduino code to try and help make the transfer a little bit more smooth. The microcontroller transmits data to the PC by the USB serial communication, and along with this, unforeseen issues is the IMU capturing data correctly on the display monitor. We had a lot of issues trying to get correct data flowing from Arduino to Unity.
Here are design results using the game engine Unity to animate the hand by interpreting input control signals as movements. Our implementation, Unity reads the communication port and sends the control signals to each joint. The virtual scene allows user to interact with physical objects in real time. Our unforeseen issues in this is the rotation vector orientation for the wrist and forearm wasn't exactly how we figured it would be, and calibration and version control. So, and yeah.
And this is a visualization of the data packet that was going from the Arduino to the virtual hand. And then this is just a couple images showing the development of the hand model, which we used Blender to develop with. And then here are a few clips showing the Unity scenes that we have. All of these videos show the hand with dummy data, which is just trying to imitate what information might be coming in. Up next, we have a demonstration of our final project.
So in this video on the left, as you can see, as he's moving his hand, it is mimicked on the screen. You can make a fist and move each of the fingers, and that is mimicked. Although one of the issues that we did have because of the IMUs is some of the movement when the hand was moving side to side was inverted rather than how it should have shown up. And then in this video on the right, it gives a clear picture of what the apparatus really looked like and how the IMUs were mounted, how the flex sensors bend to really capture that data.
Next up, we have the conclusions and recommendations.
For our project completion with functionality, we feel that we had roughly 95% of the project functionally complete. Our flex sensors, including the 2 quick flex glove controllers, did give consistent data each time we ran our program. The motions that we wanted mimicked were mimicked after we had smoothed the data out to make it less noisy. Our IMUs, though, were the issue. They weren't completely functional because they did not power up and receive data every single time that we ran our program. Sometimes we would have to plug the microcontroller in, unplug it, plug it back in to get it to work. The movement of the hand and wrist also seemed to show up as inverted on our Unity program as seen in the video. This could have been an issue with our Unity program, but it also could have been because the IMUs weren't relaying the correct data. We weren't sure if we really just needed to change how Unity was expecting to receive the data, or if there really was something funky going on with those IMU sensors.
For the performance of the project, our system performed at about 90% of what we hoped for. We didn't get exactly what we were shooting for, but we got most of it. The shortcoming in performance is the range of motion that we can mimic and the tolerance of that reproduced motion. Finger joints needed moving average to smoother sensor data, and IMUs needed attention to orientation to perform correctly. Also, the system does measure range of motion for each joint in the hand and mimics that data with reasonable accuracy, and it also replicates the user's motion in real time.
Finally, our project is about 80% operational. Even though our system meets all of the operational requirements, it doesn't always successfully operate at each startup. The issue here is with our IMUs connecting. We were close to tracking down the solution, but didn't end up having time. But in the end, our system is safe, usable, non-intrusive, and operates indefinitely after a successful startup.
For possible future designs, one could be implementing a mechanical hand rather than a virtual hand. It works similarly and have similar features, but it would be a little bit more better result of the mimicking the human hand and having that robotic hand with other sensors and parts. An addition would be to have the design with the sensor apparatus to be enclosed and include more of the user's forearm to allow for better IMU results, which would allow more accuracy. It'd also be helpful to find a more reliable sensor to replace the IMUs, just maybe a better, more reliable IMU other than the one we used. We'd get better data input and could be created in a game with using the virtual hand. And then on reflection with the lessons learned, make sure to always check hardware for compatibility before ordering. Allow time to learn software, especially with the C# Unity code and some of the Arduino stuff. Do a more in-depth research on reviews from previous customers rather than getting most of your information from the seller's website. be open to more than one solution and listen to teammates. We avoided many risks by sharing knowledge and honestly considering each other's ideas. And because of this, our project went by a lot smoother, and we were able to actually take input from each other without having to learn from failures.
Thanks for watching. That's our project demonstration.